Good morning. So today we're going to talk about two very useful formulas which collectively are combined into what we call Bayes' theorem. Now normally in order to motivate the students right away, I'd like to start with an example before I state the main theorem. In this particular case, it's probably better to just state the theorem, just explain it at the general level how it works. And then we're going to move on to two examples that you should go slow on them just to make sure I understand not only how the example is formulated, how you set up the information in a schematic way, and then finally how to recognize when the Bayes' theorem actually is necessary to use in order to answer the question. And just by looking at those examples, you will probably appreciate how useful is this theorem. So let's just state it. We have, as usual, we have a sample space denoted by S. And suppose we have a partition A1, A2, AN of S. These are events that, remember, are mutually exclusive, and then the union form the entire sample space. So the partition of a sample space means that the union of all these events is the whole thing, the whole sample space, and the intersection of any two of them is the empty set. So any two of them are mutually exclusive. And then suppose we have another event, E. Then the two formulas that constitute this Bayes theorem, so the Bayes' theorem. So the first formula states that the probability of AJ given E is equal to the probability of AJ times the probability of E given AJ divided by the probability of E, where again J can be any of those events, A1, A2, AN. So J can be any number from 1 to N. I'm going to pause for a moment. Well, actually, let me state the second part of the theorem. So the second part, it's a formula in terms of conditionals for this denominator, P of E. So the probability of E is the probability of A1 times the probability of E given A1 plus the probability of A2 times P of E given A2. And then all the way up to the last one, the probability of AN times the probability of E given AN. So this is what collectively constitutes the Bayes' theorem. Now, let me put a remark here, and then I'm going to illustrate why what the theorem states just by drawing a schematic of a typical sample space. The important thing to notice, so first of all, let me put actually two remarks here. So the first remark is that basically you have the probability of the event E in terms of conditional probabilities. With respect to the events in that partition, A1, A2, AN. So in many applications, and you will see immediately with my first example, the data is given in terms of conditionals. And once you see the example, you will realize why you could see in many applications, typically the data given in terms of conditionals. And then another important remark, if you look at the first formula over here, that means you can compute. So this formula allows you to compute one conditional probability in terms of the reverse conditional. So in other words, imagine that P of E given AJ is given. Okay, so imagine the data is given in terms of these conditionals, but you need the reverse conditional, P of AJ given E. Okay, so these two, this second bullet point, these remarks encapsulates the essence actually of the usefulness of this formula. You have the data point. Imagine the data point is given in terms of these conditionals. Imagine also you know the probabilities of that partition, right? That A1, A2, AN. But you need some information that suggests the reverse conditional. So you want not only the probability of any event E, right? So that the second part of the basis theorem allows you to compute the probability of any event E. But you may also want to compute the reverse conditional, AJ given E, when you actually have the probability of AE given AJ. So I'm not going to prove this formula, but I just want to illustrate how the events and the partition look like when you illustrate this theorem. So, you know, suppose this rectangle over here is the whole sample space. And because A1, A2, AN form a partition, imagine that this sample space is split into N pieces. So you should basically think of the event E. So because A1, A2, AN form a partition, then the union, you know, gives you the entire sample space with non-overlapping pieces, right? Because like I said, these events in the partitions are mutually exclusive. So a typical event E will typically overlap some or all of these pieces in the partition. So this is the event E. And here are the overlapping parts with the partition. So if you think about it, this event E is made of non-overlapping pieces. The common part with A1, right? So E intersection A1, this is the piece here. The second piece is E intersection A2. And then the last piece is E intersection AN. And these are also mutually exclusive, right? All of these are mutually exclusive because A1, A2, AN are mutually exclusive. So the overlapping part with the event E, those overlapping parts are also mutually exclusive. So when you take the probability of E, you can add the probabilities of these intersections. I'm basically kind of proving essentially the second part of the basis theorem. You should know from previous sections how this relates to the conditional. So remember, P of E intersection A1 can be written as P of A1, P of E given A1. The second one is P of A2, P of E given A2. And dot, 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 P of AN, P of E given AN. By the way, you don't need this part here. What I just wrote right now is just like the proof of the second part of the basis theorem. I think it's just useful to basically visualize it, how it works. We're going to focus starting with the next page on how we actually use this, this very useful formula. So with that in mind, on the next page, I'm going to state again, I'm going to write again these two formulas, and then we're going to move on with an example right away. So stay tuned for the second page. Okay, so I know it's a lot. I hope you don't get scared once you move to this page. So I have a slightly longer example that I want to go over. And I'd like you to take your time, of course, to write it down. I wrote again the basis theorem over here, so I can have it in front of me. And then please pause the video, write down the problem, or you can first listen to me reading the problem, but at some point pause and write down the full text of the problem, or you can just write schematically the data, however you prefer, but just make sure you write down the data in this example. So let's read together what we're talking about here. So suppose we have a group of students that is split according to whether they're freshmen, sophomore, and juniors. Just to make it simple, we're excluding the seniors. Notice that the split suggests that these are all of them, right? So, I mean, even if I didn't say seniors are not included, it's pretty obvious that this group that we're looking at are made of just freshmen, sophomore, and and juniors, because the percentages of each add up to 100%, right? So we say we have 50% freshmen, 30% are sophomores, and 20% are juniors. And so they add up to 100%. And then we have that the probability that a freshman passes a class is 0.3, that a sophomore passes a certain class is 0.4, and that a junior passes a class is 0.8. So let's pause for a moment. It's extremely important to understand that what you are given here are conditional probabilities. They don't say in the problem that a student randomly selected passes or fails the class. It tells you that a certain type of category of students passes the class. So the fact of the matter is the data is given in terms of conditionals, and you can understand why in many cases data is given that way. For example, one can predict that freshmen have a harder time with that particular class, and then based on the data we have, then we can provide the probability. Same thing for the sophomore and the junior. So the fact of the matter is in many practical applications, you are given a conditional as the initial data. For example, to digress a little bit, in the medical field, you many times have these conditionals. For example, they would say the probability of getting lung cancer for a smoker is this. So therefore you are given a probability of getting that disease given that the patient is a smoker, for instance. And then we're going to move on to the questions asked in the problem right away. But one practical way, which I strongly encourage to start with when you solve these problems involving the Bayes theorem, is to write the data in what we call a tree of conditional probabilities. So imagine that this tree starts with the root on the left, which denotes the sample space, which in this case are all the students in our problem. And then this sample space in these types of problems is split into three, or I mean in this case it's three, but it's split into a partition. So notice that a randomly selected student, a typical student, is going to be either freshman, sophomore, or junior with a certain probability, right? But these form a partition. And because there are 50% freshmen, the probability that a typical student is a freshman is 0.5. So you can illustrate this partition by drawing branches of these three, pointed to all the members, all the events in the partition, so to speak. So here we have freshman with probability 0.5. So write down the probability on the tree itself, right? So a student is a freshman with probability 0.5. It will be a sophomore. He or she will be a sophomore with probability 0.3 because there's 30% of them. And a typical student is also a junior with probability 0.2. When you apply the Bayes theorem, basically the events freshman, sophomore, or junior are those denoted by A1, A2, A3. Just to use the notation in the formula. Later on you can use other letters, but for now use the notation in the formula. So in other words, you know that the probability of a typical student to be a freshman is 0.5, the probability of a typical student to be a sophomore is 0.3, the probability of a typical student to be a junior is 0.2. Okay, later on, the problem gives you, I mean not later on, but in the next sentence, the problem tells you these conditional probabilities. So let's just denote, I'm going to write it here, let's denote by E the event that a student passes the class. We're going to concentrate on this event basically, right? Because all of the questions which we're going to read together, A, B, C, D, all of them talk about whether the student passes the class or not. And look carefully here. The first information here is that the probability that a freshman passes the class is 0.3. That's like saying the probability of E given A1 is a 0.3. So given that the student is a freshman, the probability is 0.3. Given that the student is a sophomore, that is E given A2, is 0.4. Given that a student is a junior, which is given by A3 in my notation here, the probability is 0.8. Okay, so we can further branch out this tree of probabilities into, for each A1, A2, A3, into passes or not passes. So passes the class, which is event E, fails the class, which is basically the complement of E. So you can write it like that. So notice that if a freshman passes the class with probability 0.3, obviously the student, the freshman, will fail the class with probability 0.7, which, remember, adds up to 1, right? So in other words, given a freshman, assuming that the student is a freshman, that student either passes or fails. The problem says that the student passes with probability 0.3, so obviously the complement failing will be with probability 0.7. So you have to basically make that difference in your mind so that you can write the correct conditional probability. The same thing for A2, right? So given that the student is a sophomore, the student will pass, again, that's event E, with probability 0.4. The student will fail with probability 0.6. And that's, again, the complement of E. Finally, assuming the student is a junior, he or she will pass the class with probability 0.8. That's event E. And then the complement up to 1, 0.2, that'll be the probability of failure of the class for a junior. So before we even move on to write down what the problem will ask us to do, let's actually make sure we understand how you write this tree of probabilities. So again, the root of the tree is the sample space. Imagine the whole set. That will branch out into 2, 3, 4, whatever the problem states, into a partition. So the sample space is split into a partition, each of them with its own, each event in the partition with its own probability. And then you have conditional probabilities assuming each of these members in the partition for a certain event, like in this case, you know, whether a student will pass the class or not. Okay. The first question is a direct question of the Bayes theorem, right? So we have a partition and the question is find the probability that the student, a student selected at random, passes the class or not. So basically the question in part A, in part A is the probability of E, right? By E meaning whether a student passes the class or not. So the data is given in terms of conditionals. You just want to know if I pick a student at random, does he or she pass the class or not? And so this is a direct application of the second part of the Bayes theorem, right? You simply write down that this is the probability of A1 times the probability of E given A1 plus the probability of A2 times the probability of E given A2 plus the probability of A3 times the probability of E given A3. Schematically, if you look at the tree of probability, you go by each branch. So the first probability of passing is via a freshman. So that's going to be 0.5, the probability of being a freshman, times 0.3, the probability of passing. The second option, the second possibility of passing is to be a sophomore. So 0.3, probability of being sophomore, times the probability of being passing if you're sophomore, so that's 0.4. And then finally 0.2, which is the probability of being a junior times the probability of passing if you're a junior, which is 0.8. So use the calculator to check, but the answer to this computation is going to be 0.43. So that is the probability of passing the class in this group. Look carefully at part B and C because I purposely, one of them is actually straightforward. In fact, pause the video for a moment and see which questions in part B or C. It's actually very easy. So in part B, I ask, what is the probability that a sophomore passes the class? And in part C, the probability that a student who passed the class is a sophomore. These are two conditionals in reverse, one the reverse of the other. Okay, so assuming you thought about for a moment, you should realize that in part B, you already know the answer. That's just from the tree of probability, the way the data is given. So assuming the student is a sophomore, so find the probability that a sophomore, so assuming a student is a sophomore, that is given A2, what is the probability that the student passed the class? That's just from the tree of probability. It's already given in the problem, right? So assuming A2 was the probability of passing, that's just 0.4. So it's very important to recognize when the conditional asked in the problem is already given in the problem. So that's coming from the tree itself. But I put this side by side to recognize when we need the basis theorem. So notice that the part C says, assume that the student actually passed. So given E, remember E denotes the event that states the student passed. So given E that the student passed, what is the chance that that student actually is a sophomore? So this is asking precisely the reverse conditional than the one given. And this one deals, look at the corner here on the left, this one deals with the first part of the basis theorem, which gives you the conditional in terms of the reverse conditional. So P of A2 times P of E given A2 divided by P of E. So P of E is needed as well in terms of these conditionals, but we already computed it in part A. Okay, so to answer the question here, P of A2, that's going to be 0.3. P of E given A2 is 0.4, which is given. And P of E, we computed it before with the second part of the basis theorem, that was 0.43. Use the calculator and this should be 0.279. Let's do part D together. Find the probability that a student who fails the class is a freshman. So this one, using our notation, is asking the probability that the student is a freshman, so the probability of A1, given that the student failed. So given the complement of E. Here we're going to use both parts of the basis theorem. So look carefully here. On one hand, from the first part of the basis theorem, that's probability of A1 times the probability of the reverse conditional failing given A1 divided by the probability of failing. So I'm gonna replace this with numbers immediately. But now on the denominator, the probability of the complement of E needs to come from the second part of the basis theorem. So remember, everything should be written in terms of the conditionals we have in the problem. All we have in the problem are the probabilities of the events that form the partition, freshman, sophomore, junior. And then we only have conditionals assuming A1, A2, A3. So that's why we can't compute P of complement of E directly. We have to go via the basis theorem in terms of those conditionals. So look again on the left corner, the probability of the complement of E is going to be the P of A1 times P of the complement of E given A1 plus P of A2 times the probability of the complement of E given A2 plus the probability of A3 times the probability of complement of E given A3. Okay. I don't have actually, I for this paper, I misaligned it because that's why I didn't have room on the right hand side. So now we can get these values from the tree of probabilities, right? So P of A1, again, that's 0.5. P of the complement of E given A1, you're looking, so pay attention here to the tree, you're looking at this branch. Probability of failure given A1, which is 0.7. And then on the bottom, again, probability of A1 times the probability of E given A1, complement of E given A1. Pay attention to the second branch here. Probability of A2, which is 0.3. And now probability of failure given A2, that's going to be 0.6. And then finally look at the last branch, probability of A3, that's 0.2. And probability of failure given A3, that's going to be 0.2 again. All right, so if I use the calculator, this should be 0.35 on the top, divided by 0.57 on the bottom. Altogether, these two, the ratio of the two is 0.614. Okay, so we're going to have another example on the last list, in the second page. Make sure you go slow on this, especially, so it's not a big deal, like with many problems in the probability theory, notice the computation is very short, right? But it's extremely important to understand which conditionals are given and when you need to compute the reverse conditional. So take your time to write this probability 3 using the notations in the formula before you jump ahead to solve the actual problem. So stay tuned for the last page. All right, so let's talk about this second example. Once again, you will have to pause the video at some moment to make sure you write this down carefully and then you follow up with me. This example, although it's one of those boring examples with the marbles, I think it's still interesting because it shows again the power of this Bayes' theorem, without which it's very difficult to imagine how you would make these odds, how do you compute these probabilities that the problem will ask you to compute. And then another interesting thing about this example is that the assumptions that you need in the Bayes' theorem, which I forgot to write down, I'm going to write down again the Bayes' theorem here after we comment on the problem, but the partition aspect of the problem, the fact that you need basically the sample space to be split into a partition, it's not immediately given. I mean, it's kind of implicitly understood. Also, the probabilities of that partition are not stated, but they can be inferred from the problem itself. So let's read the problem together, fill in the data in the table, and then we're gonna solve it together. So suppose we have 3 boxes containing either red or blue marbles. As shown, it's kind of messy here, so as shown in the table below. And pay attention to the experiment. 1 box is chosen at random and 1 marble is drawn from it. Okay, so you pick a box at random and then from that box you choose a marble at random. So let's write the data in the table here. Let's say, so we're going to write down the content on these boxes by row. So we're going to call those boxes A1, A2, A3. And then let's say A1 contains 5 red marbles and 10 blue ones. And I'm going to put the total here because I'm going to have to compute the probabilities as well. So we're going to have 15 total marbles. In the second box, we have 2 red, 6 blue. So we have 8 total. And let's say in the last one, we have 10 red and 2 blue marbles for a total of 12 marbles. And like I said, just for the record here, you have it in the formula sheet, but let's state again the Bayes' theorem. which says that if A1, AN form a partition, then the theorem states that the probability of AJ given E is equal to the probability of AJ times probability of E given AJ divided by P of E. And P of E itself, let's write it here, can be written in terms of these conditionals. Oops, I switched this, but so it's P of A2 times P of E given A2, P of AN, P of E given AN. All right, so we have this for reference. And now let's see how we can answer the question. All right, so we're going to do a tree of probability here, but notice that when I say that I select a box at random, that is the partition essentially. So the partition means that the marble that you ultimately extract comes from either box A1, A2, A3. So when you write the tree of probability, you're going to have, just like before, three branches. I'm gonna make a room here for the further branching out, right? So you have three branches, depending on whether you extract the marble from box A1, A2, and A3. Now, what is the probability of each of them? Well, the problem suggests that each of them is equally likely. So it doesn't say that you're more likely to choose one box versus the other. So you have three boxes in front of you, you pick one at random. It is implicitly understood that these probabilities are equally likely. So you're equally likely to extract either A1, A2, A3. There's three of them. The probability should add up to 1, which means that the probability of A1, A2, A3 is 1 over 3. So the problem itself suggests that you are equally likely to choose either box, right? A1, A2, or A3. So that's why you write 1 over 3 as the probability of either of them. Okay, now let's denote by E the event that a red ball or a red marble is chosen. So a red marble is chosen. Now we can compute the probability, the conditional probabilities, looking at the content of each box. So pay attention here. Given that you extract the marble from A1, what is the probability that that marble is actually red? So that's going to be 5 over 15. 5 over 15, that is the probability of event E, which is, again, a red one is chosen. And by default, the probability of the complement, which in my case, since there are only two colors, the complement is basically a blue marble. That's going to be the remaining 10 over 15. So again, the conditional probabilities can be computed now from the table itself. Assuming that you extracted the marble from the second box, A2, what is the chance that it is red? Well, there's 2 red ones out of 8 total marbles. So that's 2 over 8. And then the complement, of course, is going to be 6 over 8. Finally, if you extract the marble from the third box, there's 12 of them, of which 10 are red. So 10 over 12 is the probability of being red. And then the complement, 2 over 12, it's the probability of being blue. So again, given the way the problem is formulated here, the complement E means that you extracted a blue marble. So once you establish the tree of probability, just like before, we're going to answer the question, what is the probability that the marble is red? That's the probability of E, which according to the Bayes theorem, this is probability of A1 times the probability of E given A1 plus the probability of A2 times the probability of P given A2, and then P of A3, P of E given A3. So look at the probabilities on the tree. So that's 1 over 3. E given A1 is 5 over 15 plus 1 over 3 times 2 over 8 plus 1 over 3 times 10 over 12. Once again, using the calculator, this should give you 0.47. Part B asks you if what's the probability that the marble is blue. Again, just because there are only two colors, to say that the marble is blue is to say that it's not red, right? So that's a question of the complement, P of E complement. So again, according to the Bayes theorem, P of A1, P of complement of E given A1, A2, E complement given A2, A3, E complement given A3. By the way, I just illustrate this how the theorem basically works, because you could basically find it much faster just by taking the difference between the previous one, because these are the only version, right? I mean, if it's not red, it's going to be blue. So if the probability of being red is 0.47, the probability of being blue is just 1 minus 0.47. But I just want to illustrate how you work it out with the Bayes theorem, right? So again, from the tree, this is going to be 1/3 times 10 over 15 plus 1/3 times 6 over 8 plus 1/3 times 2 over 12. And then finally, this will be as expected 0.43, right? So the difference from 0.47. And then finally, a question on the reverse conditional. Let's read it carefully. Part C states, what is the probability that the marble is red, knowing, pay attention to the meaning of this word, knowing that it came from the second box. So what follows after knowing is the given part, right? So this is going to be a conditional in which what's given is that it comes from a second box. So given A2, what's the probability of being red? That is P of E given A2. Whereas the problem gives me conditional probabilities in terms of A1 given E given A1, right? So what you have in the table again is E given A1, E given A2, E given A3. And then the question here is, oops, the other way around. A1, no. I'm getting myself confused here. So that's correct. E given A1, A2, A3. Knowing that it came from a second box. No, this is incorrect here. Sorry about that. P of is red. No, I mean, I think I'm that it came from the second box. I actually, sorry about that. I formulated part C wrongly. So take that. So because part C is already given, right? So the way it was stated, probability of the marble being red, knowing that it came from a second box, right? So the probability of E given A2. So that's already given in the box. What I meant here, let me write it here. So the probability that it came from A2 knowing it is red. Okay, so please change that part C with, because that's what I meant. So what is the probability that it came from the second box, given that the marble is red? So what I'm asking is the probability that it is from A2, given that given E, right? Given that the probability the box, excuse me, the marble is red. Okay, because again, like I said here, you are given in the tree these probabilities, E given A1, E given A2, E given A3. These are already given. So I mean, in other words, what I wrote in part C already in the beginning, that was just E given A2, which is basically 2 over A. So what I'm asking here is the reverse probability, which requires the first part of the basis theorem, right? Which is the probability of A2 times the probability of E given A2, and then over the probability of E. So P of A2 again is 1 over 3. E given A2, that's going to be 2 over 8. And then the probability of E, which we computed before, 0.47. And then altogether, this should be approximately equal to 0.18. Okay, so sorry about that part C. Once again, what I meant is the opposite, right? So the probability that the marble came from A2 knowing that the marble was red. So essentially reversing the assumption in what's actually known about the marbles, right? So in the data, in the problem to begin with, we know the probability if we know which box comes from. Now we reverse that and we ask what is the chance that it came from a second box, for example, knowing the color of the marble, or in this case, event E. Okay, so that's all I have for the basis theorem. I'll see you next time.